Bismillahirrahmanirrahim. Assalamu alaikum students. How are you? I hope you will be fine and doing well. And I hope you have studied all the previous lectures uh, about these topics of the electrostatics that we are dealing with in these days. We are dealing with different aspects, different phenomena of electrostatics, of electromagnetic theory, and one of them is molecular field in a dielectric media. You know what is dielectric? Dielectric is basically a medium, material that produces polarization when placed inside the electric field. So we are going to discuss today the molecular field in a dielectric. We will consider a specific point inside the material, and we will see the effect of different electric fields that are that are produced inside the material due to external electric fields and inherent electric fields of the molecule as well. Then the electric field that is responsible for polarizing a molecule of the dielectric is called the molecular electric field, EM. So this is the basic definition of the molecular electric field. What is that? The field that is responsible for polarizing a molecule of the dielectric is called the molecular electric field. Means the field that you apply on the molecule of the dielectric medium and it gets polarized only a molecule of the medium. Then that electric field will be called the molecular field, EM. Or in another way, you can define this molecular field. The molecular field is the electric field at a molecular position in the dielectric and is produced by all external sources and by all polarized molecules in the dielectric within the with the exception of the one molecule at the point under consideration. This is a detailed definition of the molecular field. Means all the external electric fields that applied to the you have applied to the dielectric medium, and the inherent fields produced by the point P inside the dielectric, and the sum of all the fields. Exception is there. Exception is what? The only domain, the area that you are considering inside the dielectric, by excluding only that point, all the fields will be molecular electric field. Let us suppose that a thin dielectric sample has been polarized by placing it in the uniform electric field between two parallel plates that are oppositely charged. So we have two parallel plates, two metal plates, and a dielectric is placed inside that plates and has been polarized. That we can see in the figure over here. This is a figure that explains the dielectric placed inside the metal plates. One metal plate is positively charged, is connected with the positive terminal of the battery, and this plate is connected with the negative terminal of the battery, and this is the dielectric medium placed inside the metal plates. And we can see from this figure that all the molecules are polarized. Polarized in what sense? The positive ion has been attracted to the negative plate, and the ion, negative charge has been attracted to the positive plate. You will say positive ion and negative charge, because positive ion consists of the nucleus and the negative charge is just the electron outside the nucleus in the extra area of the nucleus, surrounding of the nucleus. So this is what I'm saying, that this dielectric medium is placed between two parallel plates. Then we come to the point, it will be assumed that the polarization is uniform on a macroscopic scale. That is, delta P is equal to 0, and that P is parallel to the field producing it. So we will say that inside the material, at the specific point, at this point, P delta P will be equal to 0. Del dot P, divergence of the polarization, will be equal to 0. The part of dielectric outside the cavity may be replaced by a system of polarization charges as shown in figure P, where the electric field at the center of the cavity may be written as from this figure. All the all the dipoles have cancelled to each other. Like this positive will cancel this negative, this positive will cancel this negative, and this positive will cancel this negative, this positive will cancel this negative. All the inside of the dielectric, all the charges will cancel to each other opposite charges. The only charges that will be left are negative charges of the dipoles on left side, means due to the positive attraction of the positive plates, the only negative charges will be left over here, and the positive charges will be left on this plate. I mean, the in the internal side of the plate, positive charges will be stored, and the external side of the plate, negative charges will be stored, like in this figure. You can see these charges are the charges that we stored due to the external battery, and these are the induced charges due to the polarization of the medium. All other charges inside the material have been cancelled each other. Then the net electric field EM will be, the molecular electric field will be equal to EX plus ED plus ES plus ES E prime. Now we will see what are these EX, ED, ES and E prime. The EX is the primary electric field due to the charged parallel plates, means these charges, electric field due to these charges. This is a primary field, means applied field. ED is the depolarizing field due to polarizing charges on the outside surface of the dielectric. The electric field due to these charges. These are the depolarizing charges. These are the depolarizing charges. Positive, positive, positive stored outside of the dielectric but inside of the plate. Outside of the dielectric medium but inside of the plate, these charges have been stored, and the electric field due to these charges, positive and this series of the negative charges, is called the depolarizing electric field and is written by ED. ES is due to polarization charges on the cavity surface S. This is the cavity that we are considering, and the charges stored on this cavity have the electric field ES. Now we can see that why these positive are stored on this cavity, because inside the cavity on these are the dipoles, and the dipoles have the negative charge on the left side, therefore the positive from outside will be stored on this cavity. And E prime is due to all of the dipole inside of S means inside this surface, all the dipoles, the left dipoles that have electric field E prime. Therefore, the depolarizing electric field ED can be written as minus 1 over epsilon naught rho using the Gauss's law. And since the normal component of the electric displacement D is continuous across a vacuum dielectric interface, what is the vacuum dielectric interface? Look here. This is the dielectric medium. This is the outside of the dielectric medium. And this is the vacuum. And this interface is the vacuum dielectric interface. And the electric displacement is continuous at these points. There, and we know that D is equal to epsilon naught T. The electric displacement is given by epsilon naught E in the vacuum just outside the dielectric slab. Therefore, E will be equal to Ex plus T. The electric field will be equal to Ex plus Ed. E what is E? E is the macroscopic electric field in the dielectric and is sum of the two fields Ex and Ed. Now we can use equation number 3, 2 in equation number 1. We will get total electric field, molecular electric field Em is equal to E plus Es plus E prime. And then the field Es arises from polarization charge density sigma p and is equal to Pn. We have studied the Pn is also the polarization density on spherical surface S. So we can use the spherical polar coordinates if this is the spherical surface, and therefore we can use the spherical polar coordinates. Using the spherical coordinates and taking the polar direction along the direction of P as shown in the figure C. If this is a sphere, this cavity has been considered as a sphere, and at the sphere the charges are stored in the opposite direction and the direction of the polarization has been considered to the direction of the P. This one. This is the polarizing, this is the angle theta. Then in the spherical polar coordinates, we know that there are three types of coordinates, r, theta and phi. We can write this electric field in terms of dE S is equal to minus P cos theta over 4 pi epsilon naught r square r dA. And we know that r square sine of theta d of A, this area, differential area, d of A is equal to r square sine theta d phi. We can put the value of dA over here and we get Es is equal to 1 over 4 pi epsilon naught P integral 0 to pi d phi 0 integral 0 to pi cos square theta sine theta d theta. And by solving these integrals we get 1 over 3 epsilon naught P. This is our equation number 6. Now we will use it in equation number 4. We have Em is equal to E plus Es plus E prime. Using the value of Es over here, we get Em is equal to E plus 1 over 3 epsilon naught P. E prime will become 0. We will eliminate it. Only the two terms will be left, E plus Es, and putting the value of Es from here 1 over 3 epsilon naught P, we get Em is equal to E plus 1 over 3 epsilon naught P. The dipole moment of a molecule is proportional to the electric field acting on it. This is the very established point that dipole moment of a molecule is always proportional to the electric field applied on it that is producing that dipole moment. And the ratio of the dipole moment of a molecule to the polarization is called the molecular polarizability. This is another definition that we have over here, molecular polarizability alpha. What is that? The ratio of a dipole moment of a molecule to the polarizing is called the molecular polarizability alpha. So, according to this definition, the molecular polarization is directly proportional to the electric field E, and if you put the a constant, proportionality constant over here, then it will become Pm is equal to alpha Em. And if there are n molecules per unit volume, then polarization P is equal to nPm. This is the Pm for a single molecule, and if there are n molecules, then the total polarization P will be equal to n multiplied by this polarization Em. Means it will be equal to n alpha Em. And now we will combine this equation number 8 and this equation number 7 with this result. Then P will be equal to n alpha. We will put the value of just Pm over here, n alpha, and instead of E, m, we will write this value of Em from equation number 7 over here. This will become n alpha into E plus 1 over 3 epsilon naught P. And this equation may be rewritten in terms of the dielectric constant K, since P is equal to chi E. This is the equation that we have studied in our previous lecture, that polarization is directly proportional to electric field. Then P can be written as chi E, or is can be written as K minus 1 epsilon naught E. So equation number 9 will become now, if you just put the value of P over here, K minus 1 into epsilon naught E is equal to n alpha into E plus 1 over 3 epsilon naught P. And if you will rearrange this equation, and you will get the alpha is equal to 3 epsilon naught into K minus 1 over n into K plus 2. This will be our equation number 10 and is known as Clausius-Mosity equation. This relation is called Clausius-Mosity equation. So this was our today's target, to discuss the molecular field in a dielectric and derive the Clausius-Mosity equation. If you have any question regarding this topic, today's topic, you can ask me. And if you have the question later on, you can ask me why my WhatsApp number is given in my description. And thank you very much for today's lecture.